So welcome everyone to the first fall seminar of our APS GPC seminar series, which is a seminar series meant to introduce the physics community to various aspects of the climate system, including the latest results and outstanding questions and challenges. And just as a reminder, for those of you who haven't checked out our website, we have all of the talks recorded. The recording's available, including upcoming talks and the listing and link to register there. I've posted that in the chat for you to take a look at. So for today, it's really a pleasure for me to introduce our speaker, Professor Allison Wing, who is an associate professor in the Department of Earth, Ocean, and Atmospheric Science at Florida State University. Allison received her PhD from MIT and followed that up with a postdoc at Columbia University. And she's really well known as an expert in kind of elucidating and unraveling our understanding of the tropical climate and its response to climate change. And in particular, her work on the organization of tropical convection and the mechanisms that control it, as well as in tropical cyclones, cyclogenesis. So many different aspects. And today she's going to be talking to us about the organization of convection and climate. And if you have clarification questions, please put them in the Q&A and I will prompt Allison to address those as they come. But for more substantive questions, we'll leave those to the end and there'll be time to get those answered. So with no further ado, Allison, please take it away.
Okay, thank you very much, Tiffany, for the introduction, and thank you to the GPC committee for inviting me to give this seminar. Let me get my slides up. Okay, so hopefully everyone should be seeing the full screen. So today I'm going to talk about the organization of tropical convection and climate. And I'm going to structure this talk with sort of three sections. One, sort of reviewing some of the basics of moist convection in our atmosphere. Second, talking specifically about the organization of convection. And then finally, the impacts of that organization on climate more broadly. Some of this might be familiar to you if you were at the APS meeting in March and came to the tutorial, but there's some new things in it as well. And so without further ado, we'll get started on the basics of moist convection. And so I actually like to start talking about convection by talking about what the atmosphere would look like if there was not any convection going on. And this is considering a state of radiative equilibrium, where basically, the only sorts of enthalpy fluxes that we have in the atmosphere are radiative ones. And so radiative equilibrium is then that equilibrium state that the atmosphere surface system has in the absence of non-radiative enthalpy fluxes. And so we have, shortwave radiation from the sun that is absorbed by the surface and atmosphere and heats them. It can also be reflected by the surface and atmosphere or things in the atmosphere. And then the surface and atmosphere cool by emitting long-wave radiation. And collectively, the net between those two drive the actual state of the atmosphere, or try to drive it towards a state of radiative equilibrium. The exact properties of this equilibrium depends on the composition of the atmosphere. So what types of absorbing and emitting and reflective properties, gases that we have. And we have the fact that radiation itself is a very non-local process. So the radiative heating at any one level in the atmosphere depends on what's happening at other levels as well. And so what does our sort of basic structure of the atmosphere look like in the state of radiative equilibrium? So this is a plot from Manabe and Strickler in 1964. Of course, Manabe, who won the Nobel Prize in physics a year or two ago on some of this exact work. So this is showing temperature as a function of altitude or pressure. And this is based on doing, one single column calculation, but using, a real radiative transfer model to do that, where radiation is really the only thing going on. And so this is the sort of temperature structure that we get. And some things about it are right. We see that the temperature is decreasing with altitude in this lower part of the atmosphere known as the troposphere, and then it increases with altitude in the stratosphere because of the ozone layer there. But there's also things that are not quite realistic. In particular, if you look at the surface temperature you get, that's sort of 330 something Kelvin, which is way too hot. Our global mean surface is warm, but not that warm. And then our troposphere, tropopause, the cold point here is too cold. And so in combination, our lapse rate, or the decrease of temperature with altitude, is too big. And the reason that this is wrong is that we are missing a key ingredient for our troposphere in particular, which is convection. On the other hand, our stratosphere actually looks kind of okay. And so it turns out radiative equilibrium is a reasonable approximation for the stratosphere, but in the troposphere, we need to include this missing ingredient of convection. And the reason that we need to include that is that it turns out that this radiative equilibrium temperature profile is very unstable to convection. And so if this happened, it wouldn't persist for very long. We would start to have convection occurring. And so what is convection? I'll start by talking about dry convection. And so convection is small scale thermally direct circulations, which result from the action of gravity on an unstable vertical distribution of mass. And dry convection is simply convection without a phase change. And so this does not actually require that the convective fluid be air. If you're boiling water on your pot in the stove, even though it's water, which is wet, of course, in terms of the properties of convection, that's actually dry convection, at least until you start to actually have it boil and then have evaporation. And so when is a fluid unstable to convection? When does convection occur? Well, this is basically equivalent to us asking the question, if we imagine taking a parcel of air and displacing it upwards, is it going to be unstable and continue to rise upwards? That would mean it's unstable to convection and convection occurs. Or would it sink back down to its original location and be stable? That question of stability depends on whether that lifted parcel is buoyant. So whether or not it's more or less dense than its surrounding environment. If it's less dense, it'll continue to rise and be buoyant and unstable. And this is equivalent in the atmosphere to asking whether this rising parcel cools more or less than its environment does. All parcels cool as they rise due to adiabatic motions and the change in density of the atmosphere as you're rising. So you have work that's being done in the atmosphere as the parcel expands. But is it doing so more or less? Is the environment cooling more or less than what that parcel would do? So if we add that process into our simplistic picture of the atmosphere, we now have a state of radiative dry convective equilibrium, where in addition to our radiative processes, we also have turbulent fluxes of heat in the atmosphere, which transport energy upwards in the atmosphere. And so I like to think of convection as a mixing process that's kind of vertically redistributing heat and energy in our atmosphere. And it's acting to try to drive the atmosphere towards a temperature profile that's neutral with respect to that convection, to that stability. So neither stable nor unstable, which for dry convection is known as a dry adiabatic lapse rate. So we have sort of these two processes battling each other. The radiative fluxes are trying to push us to that steep radiative equilibrium profile, and convection is trying to push us towards this convectively neutral temperature profile. With these two things going on at the same time in this battle between convection and radiation, the convection wins because it's a much faster process than radiation. Convection equilibrates on timescales of an hour or so, where radiative equilibration timescales are more like a month. So that means in our radiative dry convective equilibrium state, the whole atmosphere evolves to an average temperature profile that is neutral to convection. So the action of convection occurring keeps it on average neutral. So then what Manabe did in our study was they said, all right, let's impose this as a condition in our one-dimensional modeling of the atmosphere. So this was a very simple, crude way of including convection, because they're just saying, okay, anytime that the temperature lapse rate goes unstable, we're just going to force it back to that dry adiabatic neutral profile. And so now we see the curve that they get. And we see that this is a bit better in compared to our real atmosphere. We're not quite at 340 Kelvin anymore, which is good, but it's still not perfect. Our surface is still a bit too warm. The tropopause is still a bit too cold, and the lapse rate is still too large. The reason for this is that this convective neutral state for dry convection is one in which the temperature profile matches the dry adiabat, which is around 9.8 Kelvin per kilometer. But if we look at actual observed temperature profiles in our atmosphere, they cool with height at a slower rate, more like 6.5 Kelvin per kilometer. And so the thing that's missing is that in our atmosphere, we actually have moist convection occurring, not dry convection. So the next step then is to think about, okay, if we have moisture in our atmosphere and allow it to undergo phase changes, what happens to this, conceptual parcel that's rising in the atmosphere as it's convecting? So in fact, in our atmosphere above a thin boundary layer near the surface, almost all atmospheric convection does involve a phase change of water. And the different steps are as follows. We start off with this parcel in which that it's not saturated yet. It has moisture, but it's not saturated. It rises from the surface along what's known as a dry adiabat, sort of behaving if it was dry, until it reaches what's known as the lifting condensation level, which is where saturation occurs. Once that occurs, the air is saturated and water can start condensing out. It then will continue to rise on what's known as a moist adiabat, where any excess water vapor is condensed as it continues to cool. But this has the effect of providing a little bit of warming to the parcel due to the latent heat release during the condensation process. And so this means that the total temperature change of the parcel, it's still cooling, but it's not cooling quite as much as if it wasn't having this condensational heating partially compensating. That continues until the parcel reaches what's known as the level of neutral buoyancy, in which it's no longer buoyant, which is approximately our cloud tops of our convecting clouds. So if we then add that into our sort of cartoon picture of now radiative moist convective equilibrium, we still have these turbulent fluxes of heat, but they occur, predominantly now in cloud systems, not entirely, but predominantly. We bring that into our sort of simple 1D view of the atmosphere. Again, here, very crude way was done of adjusting that by just sort of forcing the temperatures to be this moist adiabatic lapse rate, which is not exactly a constant, but it is close to 6.5 Kelvin per kilometers. And now things look much better than they did before. Our surface temperature is around 300 Kelvin, which is sort of an appropriate mean surface temperature. Our tropopause temperature is around 220 Kelvin. And obviously by design, we have a more realistic lapse rate. And so a key result of the fact that we're having moist convection is that it really allows our temperature lapse rate to be smaller than it would be without. And it cools the surface relative to having dry convection. And so we can understand some of these really basic properties of our atmosphere by just this simple view of radiative convective equilibrium. And it really shows the important role of convection in driving some of these key properties. Now, in addition to the ones I just mentioned, there are other important consequences of the fact that we have moist convection with phase changes in our atmosphere. One is that it allows that the fact that it's moist convection means that these turbulent, rising small scale motions redistribute water vapor vertically in our atmosphere. And this is important for climate more broadly because water vapor is our most important greenhouse gas in the atmosphere, absorbing and re-emitting long wave radiation as well as shortwave radiation. When we have condensation occurring in moist convection, that forms clouds, which affects the albedo of our planet and its ability to reflect shortwave radiation from the sun, and also our ability to cool via emitting long-wave radiation, as clouds are also very, very effective absorbers of long-wave radiation. It also results in a sort of asymmetry between up and down motions in the atmosphere. In moist convection, we have this characteristic of having strong, narrow updrafts or rising motion that are then widely spaced, surrounded by then broader regions of more slowly sinking air. And so this narrow up, broad down asymmetry only emerges when you have moist convection going on. And then finally, since convection redistributes water vapor, affects clouds, those things are highly impactful in the radiation budget. And then that affects temperatures, which then go back to affecting convection. Radiation and convection are highly interactive processes occurring in the atmosphere. And this allows the potential for really rich interactions and instabilities that I'll talk about more later in the talk. I'm going to focus on mostly deep cumulus convection here. We also can have shallower or stratocumulus convection. So for example, these little clouds here you're seeing in the top right picture, These are clouds that are sort of at the top of the tropical trade wind layer, maybe at 2 kilometers or so, and they're really shallow and short and tiny, and they matter for lots of things too. But the thing that I'm most interested in is in deep convection, so these cumulonimbus clouds, and then the convective systems that they organize into. And so just some of my favorite pictures that I've taken. The top right one, this was taken from the OTREC field campaign aboard NCAR's Hyper G5 aircraft of this really awesome mesoscale convective system over the tropical Eastern Pacific Ocean. Now, the fact that we can have deep convection occurring, it basically means that these convective motions and the clouds associated with them are occurring really throughout pretty much the whole depth of the troposphere. That adds other special properties and other complications to understanding and modeling and predicting convection and its effects. So this depth, again, introduces new phenomena. For example, it allows us to have precipitation. You can have precipitation from shallower convection, but it's more prevalent and heavier precipitation when we have deep convection. Also, the fact that now this is occurring up into the upper parts of the troposphere where the temperatures are much colder means that some of the clouds will be ice clouds, and we have to deal with all the ice microphysics processes, which are much more complicated than liquid or warm rain sort of microphysics. So that adds lots of interesting things, but it also makes it, from a practical standpoint, much more complicated to model, especially. And deep convection is really the type of convection that leads to the potential for severe weather. So thunderstorms, lightning, hail, tornadoes, strong winds at the surface, all the potentially damaging impacts that come with that. Okay, so that's sort of the first part, the basics, maybe a refresher for some of you, or just a hint of some of the most important things to think about for those who are not familiar with convection. Now I'd like to talk about the organization of convection, which is, really been the focus of my research in my career thus far. Here I'm going to talk mostly about organization of convection more generally, so mostly non-rotating forms of organized convection. But as Tiffany mentioned, I also do research on tropical cyclones, which you could think of as a very special form of organized convection that is rapidly rotating. And the reason that I want to talk about this is if we look at clouds and convection in our atmosphere, we find that in the tropics in particular, sometimes it's isolated or scattered, right? So you might have one nice big textbook, cumulonimbus thunderstorm cloud like this, and then, not a lot going on around it, and then maybe another one many miles away. This is what is our kind of really classical simplified view of convection in the tropical atmosphere. And it is what things look like some of the time. This is another picture from this same field campaign. So sometimes that happens. But often it's instead clustered together into organized systems. And so this is my favorite mesoscale convective systems, where now we see the whole clump or cluster of convection that's together and then forming this kind of broader circulation within it. And this organization of convection is really ubiquitous in the atmosphere, especially in the tropics. And it occurs on a variety of different spatiotemporal scales. And so, for example, at the mesoscale, things on the order of, say, 1,000 kilometers, we have squall lines where we have sort of convective cells organized in a sort of linear way. We also have mesoscale convective systems, and I'll define exactly what that is in a moment. If we move up to the synoptic scale, as I said, we have the special spinning type of organized convection, tropical cyclones. We also have equatorial waves. So this is an African easterly wave, where it's this kind of, wave-like structure associated with a sort of envelope of convection. There's other equatorial waves as well, like Kelvin waves, equatorial Rossby waves, so on and so forth. And then going up to the planetary scale, we can even think of things like the Madden-Julian oscillation, which is this enhanced region of convection, that's order 10,000 kilometers, which then slowly propagates eastward at a time scale of sort of 30 to 70 days as this planetary scale mode of organized convection. And above that, you could think, even of the ITCZ or Hadley cell itself as representing a planetary scale of organized convection. So it's really ubiquitous, lots of scale at play. And going along with that, there's a lot of different mechanisms that can lead to this organization of convection. So for squall lines in particular, interactions between the convection and large-scale vertical wind shear in the atmosphere is the main dynamic mechanism known to drive that sort of mode of organization. At larger scales, we also know that sea surface temperature gradients can drive convective organization, as deep convection tends to occur over the warmest SSTs. And so we could think again of the Walker circulation as maybe this sort of planetary scale organized convection. But we can have SST gradients playing a role on smaller scales as well. And then we can also have organized convection, such as that from these equatorial waves, associated with these, dynamical disturbances. And this could occur, I give the example here of equatorial waves in the tropics, but if we think about the mid-latitudes where we have extratropical cyclones, driven by baroclinic instability, that can be dynamic forcing for having organized convection within those storms as well. So these are just some of the different mechanisms that can play. There's more, and I'll talk about them as well. And regarding, I mentioned the vertical wind shear for squall lines. One of the other pieces of dynamics that plays into role in that and is forcing for convective clustering and organization more generally is something known as cold pools and gust fronts. And so I wanted to mention that briefly. Basically, what can happen is that you have your big thunderstorm cloud, and there's rain falling, some of that. But if that precipitation is falling into an atmosphere that's not saturated, some of it can re-evaporate on the way down, which then causes cooling of the air. That air is then very heavy because it's cold and negatively buoyant. And so it forms a downdraft, which rapidly sinks to the surface, hits the surface, and spreads out as a cold pool, producing a gust front at its leading edge. So this is sort of a cartoon view of that downdraft expanding outwards. And we can see these gust fronts at the leading edge of cold pools on satellite and radar imagery. So here's our radar image. This kind of ring of radar returns is the gust front. And then we also see cloud formation at these edges of cold pools from satellite view. And that's because that spreading cold air moves like a density current and then can trigger new convection through both mechanical and thermodynamic processes at its edge. And so cold pools and their associated triggering of new convection at their leading edges can be a forcing for generating new convection adjacent to old convection and then allowing it to cluster together. These can also interact dynamically with through vorticity dynamics with vertical wind shear in the atmosphere to form squall lines and sort of more persistent mesoscale features, which I'm not going to go into more detail now in the interest of time. But the existence of these processes, which is again occurring because we have precipitation, because we have deep convection, is something that is important for allowing convection to organize. Okay, so I like to just basically show 8 versions of the same picture because I love it so much. A very particular type of convective organization are known as mesoscale convective systems. And I love this picture so much because it's just so perfect. It's basically a textbook image of an MCS. So here's the actual picture. Here's the textbook image. They match amazingly well. And the neat thing about this is that it's not just a blob of thunderstorms that are close to each other. There's a circulation through the entire system that is larger than, any individual convective cell. And so we have this, overall updraft into this convective system, which then spreads outwards, leading to this large cirrus anvil that can reach really big sizes. And then we have this sort of mesoscale downdraft forming a cold pool. And all sorts of interesting dynamics with that. I'm not going to go through it all in detail. I just like that it was like this, even this little convective overshooting here, which is where kind of convection that has a lot of momentum as the updraft is rising up, kind of overshoots its level of neutral buoyancy. It matches up with the cartoon just so well. It's amazing. So what are sort of the, climatology of these types of mesoscale convective systems and their definition? So it's defined as a contiguous area of precipitation or sort of cold cloud tops associated with that, that's at least 100 kilometers in at least one dimension. So it could be circular, but it also could be more linear feature, like a squall line. And so this is showing the frequency of occurrence of such convective features again, with sort of different geometries in them. And you can see that they're really, this is from TRIM satellite data, focused over, sort of tropical land regions, as well as sort of the ITCZ and in sort of storm track areas. We can see there's a lot here kind of along the Gulf Stream. So these do occur both in the tropics and mid-latitudes. This, TRIM only went up to about 35 or 40. So we're kind of missing most of the mid-latitudes in this picture, but other types of climatologies have included that. They're also referred to sometimes as just generally cloud clusters or convective systems, or MCS for short, but those terms are all more or less, referring to the same phenomena. Mesoscale convective systems are of particular interest because they are one of the main types of systems that does generate severe weather events, including both, precipitation extremes as well as severe weather like, tornadic activity, things like that. And they can produce, as sort of you could see on that picture I showed you, these huge cirrus outflow anvil clouds. So that spread much further from kind of where the active convection is occurring. And so that means that even though these systems don't, these frequencies here are typically less than 10% of the time, or even far less than that, they occur, not that often, but they produce a large fraction of tropical, in particular, cloudiness because of these big, wide sort of spreading anvil clouds and cirrus shields. There's sort of several subsets of this. So squall lines is where you have a more linear feature of convection that then has a broader region of stratiform precipitation behind it. And then mesoscale convective complexes, or MCCs, are when it's a sort of more circular type of organization that has particular size and duration criteria. And so this is, the bottom is showing a satellite image. That's an example of a mesoscale convective complex. You can see it's like roughly the size of the state of Missouri. Big cold cloud shield here. The top is a climatology based on satellite data showing with the dots where these MCCs occur. We can see mostly located over land in the tropics, as well as notably the Great Plains of the United States, as well as sort of Central South America. Okay, so that's some of the types of organized convection in our atmosphere. But one of the questions that I've asked in my research, and other people as well have asked this, is that, okay, we know there's lots of different mechanisms by which convection organizes, but what if we get rid of some of those? What if we don't have wind shear? What if we don't have SST gradients? What if we don't have large-scale dynamical disturbances or other heterogeneities in our system? Can we still have convective organization? And the answer is yes. And to investigate that, we return to this sort of idealized view of the tropical atmosphere of radioconvective equilibrium. But we're going to simulate it in a full physics model where instead of just imposing a sort of, convective adiabatic lapse rate, we're going to let that, we're going to resolve convection and let that emerge, intrinsically as a property of the atmospheric system. And this is done by doing simulations with no land or sea ice, totally uniform sunlight or insolation coming in, uniform SST anywhere. These are going to be no rotation simulations. Everything's the same everywhere, and they're just initialized from random noise. And so hopefully the movie is not too jerky coming through Zoom. Basically, this is a domain that's roughly 700 by 700 kilometers in our dimension. We're looking down on the top of the domain. The gray shading are clouds. They look like they're popping out at you because the vertical axis has been stretched a lot for the display here. The colors are showing water vapor humidity near the surface, where kind of counterintuitively, maybe the blue is dry and the reds are moist. And so we can see that initially the clouds were kind of random everywhere. But now we have this dry patch devoid of convection that has formed and is starting to get drier and drier and expand. And this is triggering what's known as self-aggregation. As that's occurring, the dry regions get drier and the moist regions get moister. And convection is suppressed in that dry patch and becomes increasingly localized, first into a line, and then that collapses into a singular circular cluster. In this domain, if you have a bigger domain, you can have multiple clusters. And so this process is known as self-aggregation of convection. It's the spontaneous transition from randomly distributed to organized convection, despite the totally homogeneous boundary conditions. So again, the sea surface temperatures, everything in the initialization, the insulation is the same everywhere across this domain. There's no reason necessarily that the convection should be only in this part of the domain. And whether it's here or someplace else is just ultimately random. This self-aggregation results, it can't come from SST gradients or vertical wind shear or these dynamical disturbances. None of that is present in these simulations. Instead, it results from interactions between the convection and its surrounding environment that include processes related to clouds, water vapor, radiation, surface fluxes, and circulation. And I could give a whole separate talk just about those mechanisms, or maybe multiple talks. But just to provide a very, very quick overview of some of the different feedbacks going on, research generally agrees that the most important are interactions between clouds and radiation. We do also have a role for interactions between especially long wave radiation and water vapor, because the amount of water vapor in the atmosphere controls in part how much long wave heating or cooling that you have, and that thus spatially varies as the water vapor distribution spatially varies. Similarly, interactions between clouds. And so in our sort of moisture regions where we start to have more deep convection and cloudiness, these cool less than the surrounding less cloudy, dry regions. This leads to a feedback that leads to more convection occurring in those initial moist, cloudy regions. We also have interactions between clouds and circulation. So clouds cause spatially differential radiative heating. Spatially differential heating leads to circulations. Circulations transport properties and can help convection cluster. And in particular, the sort of cloud circulation coupling related to low clouds and sort of the regions adjacent to deep convection have been shown to be important. There also is some role for surface processes. So in particular, feedbacks associated with the dependence of surface fluxes on wind, as well as interactions between moisture and convection itself. Convection is more likely to occur in places that are already moist and acts to moisten the atmosphere. So again, lots of work done on all these different mechanisms. Now, you might be asking, okay, that was cool, but that was in a super idealized model, right? It's neat, but the problem is our real world's not like that, right? Our real world does have SST gradients. It does have variations in insulation. It does have dynamical disturbances. So is this self-aggregation thing really relevant for real world convection? Or rather, how might it manifest in the real world? So the way I think of this problem is that there's a variety of different avenues how this self-aggregation process I just showed you, how that could be manifesting in the real world. I think at minimum, we can use those idealized simulations as a tool to understand mechanisms, and then we can try to apply those mechanisms to the real world. So some possible applications are that these types of sort of radioconvective feedbacks could help lead to the initial aggregation of deep convective elements that then induce mesoscale circulations of an MCS in tropical oceanic regions. We could also have these radioconvective feedbacks amplify convection that is perhaps initially organized by other means, such as dynamical disturbances or wind shear, things like that. So it's sort of like, maybe an acceleration process, maybe not the thing kind of getting it going initially. And we could also say, well, okay, given this in an idealized homogeneous modeling environment, these radioconvective feedbacks manifest as self-aggregation, but maybe in the real world, they're helping other things along, such as tropical cyclone formation. So a lot of the group work in my group recently has shown that in particular, long wave cloud radiative feedbacks help tropical cyclones develop and intensify, and in particular, occurrence of rapid intensification is more likely when you have stronger and long wave cloud feedbacks. And there's sort of growing evidence that the Madden-Julian oscillation, the amplification or growth of that process, is also strongly influenced or even driven by these cloud-radiated feedbacks. So the structure and pictures don't necessarily look the same in the real world as they do in the idealized models, but the underlying mechanisms are acting in both. Okay, so now moving on to the last section of the talk. I just talked about how convection can organize and the different types of organization. But does this matter, basically? Is it just kind of interesting because it gives us pretty pictures? Or does it have kind of broader scale impacts on climate in particular? And we're going to consider this using evidence both from observations and from model simulations. So using observations, a lot of the work that has been done in this area has considered sort of individual convective scenes. So you maybe would choose a box of a particular size and assess how organized the convection is in that box. So for example, you kind of make a mask of where deep convection is or is not occurring. So for here, this box, this is, I think, a 5 by 5 degree box. This one here has just kind of one blob in it. So that's pretty highly organized convection, whereas this box, in this case, same size, has many more smaller scattered sort of convective features. So we would say in this case, box A is more organized than box B. It's not necessarily that one is completely organized and one is not, but rather a variation in the strength or degree of the organization or aggregation. And there's many, many different metrics that have been developed to try to quantify this. In models, I'm going to leverage a set of idealized simulations using the radial convective equilibrium framework in intercomparison that I've led. And we have two different domains in this intercomparison. One is a large domain that permits convective organization to occur. And that domain is roughly the size of this red box. That's sort of roughly the width of the Indian Ocean. It's not actually a simulation of the Indian Ocean. It's just that size, basically. And so in a cloud resolving model, this is kind of maybe what the convection would look like. In this actually idealized simulation, we have these kind of alternating bands of clouds and no clouds. In a spherical global climate model, it might look something like this. And then we also have a small domain that prevents organization, which is the size of this little blue square here, about 100 by 100 kilometers. And as judging by the example in the satellite image, that's, too small to have at least this larger scale convective organization. And so this is known as the RCEMIP project, the Radiant Convective Equilibrium Model Intercomparison Project. And we had 30 different models participate in this project and running these simulations, including cloud resolving models, global climate or general circulation models, global cloud resolving models, as well as large eddy simulations running at much higher resolution. So we can kind of compare across states of organization across that model ensemble. And there's a number of different things we can think about in terms of, does the organization, its existence, its strength, does that affect other properties of the simulated or observed climate or large scale environment? The first is one I already alluded to. Organized convection is responsible for a large fraction of tropical rainfall. So for example, using different sort of convective regimes based on observations to identify organized convection, the regime associated with organized convection contributes about half of all total tropical rainfall, even though it has a pretty low frequency of occurrence. And changes in the frequency of occurrence of this particular regime are responsible for much of the observed regional increases in tropical precipitation in recent decades. So the top panel here shows the observed change in monthly mean precip. So we have some regions where it's increasing, some where it's decreasing. And if we look at just to the contribution from the frequency of that organized deep convection regime, the patterns and magnitudes match pretty well. That's sort of just kind of looking at mean precipitation. What about precipitation extremes, the rarer occurrences of heavy rainfall? That is also strongly modulated by organized convection. So this is looking in our ensemble of model simulations where all of the different symbols here are different models. The circle ones are the cloud resolving models, the X's are the GCMs. And this is all at one temperature. And basically the models that just on average are more organized than other models tend to have higher 99.9 percentile 1 hour precipitation, which is sort of an extreme. And this is particularly true at scales sort of greater than 15 kilometers. The slopes are a little different between the two model types, but they both agree. There also is a potential role in terms of how precipitation extremes respond to warming. So our sort of default assumption, and this has been shown across a large body of theoretical and observational and other modeling work, is that precipitation extremes increase with climate warming due to greater moisture availability in a warmer atmosphere following the Clausius-Clapeyron relation. But models can disagree on exactly how much of an increase that you get. So here, same set of models from this intercomparison project. The y-axis is the percentage change per Kelvin in that 99.9th percentile of precipitation. Goes up for nearly all the models. Not sure what's happening with that one. But if we look at how the organization in those models changes with warming, that plays a role in exactly how strongly it increases. So this black line here is what we'd expect from Clausius-Clapeyron. If the model becomes more organized as it warms, that tends to give us a larger or even higher than Clausius-Clapeyron rate of increase in our precipitation extreme. But if we have a model in which convection becomes less organized with warming, we can have a slower rate or even sub-Clausius-Clapeyron rate of change. And this is related to how convective organization modulates precipitation efficiency. So how much of the condensation that actually occurs makes it to the surface as precipitation, as well as updraft strengths and sort of the dynamic contribution. Okay, so that's precip. How about the energy budget? And did I miss a slide? There should be one about clouds in here. I guess it's over there. Sorry, they're ordered differently than I expected. Okay, so spoiler alert, organized convection affects the humidity distribution and clouds, which means it could affect the energy budget, and indeed it does. This is showing radar-based estimates of heating from observations of organized convection, where the sort of fraction of stratiform convection is used as a proxy to identify mesoscale convective systems. And what's shown here is the vertical profiles of the total heating, so latent plus radiative heating. And as we shift, as deep convection becomes organized into more mesoscale convective systems, as we go from the dashed to the solid to the, dotted to solid to dashed lines, we see that these total heating profiles become more top heavy. And this is important then for sort of the circulations that are induced by this heating structure. And then if we look kind of more generally, if we think about the tropics overall and how organized it is or not using one particular metric for organization, it turns out that these more organized states, or sort of on scales of like monthly variations, have more tropospheric radiative cooling and in fact, enhanced net radiative cooling at the top of the atmosphere. So variability in the degree of organization affects our atmospheric energy budget. This is related to the fact that organization modulates both the humidity distribution and cloudiness and cloud feedbacks on climate. So thinking about just clouds themselves, this is an example from observations. This is, I think, CloudSat data showing, and it's not described here, but basically the different colored lines on this plot are just states that have different average degrees of organization. Whereas we go from the green to the red, things are becoming more organized. And if you can see, there's a sort of prominent reduction in the amount of high clouds when we have more organization. And this is from observations. Looking in simulations, we see the same sort of tendency. Organized states in models have fewer high clouds than less organized or unorganized states. The changes in low clouds are a little bit trickier. Maybe there's an increase with organization. It's harder to both measure from satellites and simulate in simulations. Okay, so that's just sort of in a given climate or a given situation, our cloud distribution changes. What about how clouds change with warming and the sort of then resulting effects of that on our energy budget? That's known as a cloud feedback. And we think about this in terms of global warming and sort of climate change, in part because how clouds change with warming is one of the biggest sources of uncertainty in terms of how sensitive the climate overall is to an external forcing like an increase in carbon dioxide. So that's what is known as a cloud feedback on climate. If it's a positive feedback, that means the clouds are changing in a way such that we would have, more warming than we otherwise would expect. If it's a negative feedback, we would have reduced warming or even cooling. And so we've looked at this across this, again, intercomparison of models, computed the cloud feedbacks in all of these different simulations. And what we found is that models that just on average have stronger organization tend to have less positive or even negative cloud feedbacks. So in general, the cloud feedback is positive. It's just maybe, or our expectation anyways, that it's positive. It's just maybe less positive or even maybe slightly negative in these models that are just have more stronger organization in general. And this is due to the impact of organization, particularly, at least in these models, on the short-wave effect of high cloud optical thickness, which is something that I think as a field, we don't really understand completely what controls that and how it changes with warming. Okay, so then the final thing is, all right, organized convection affects the clouds, it affects the precipitation, it affects cloud feedbacks. What about climate sensitivity overall? Does the degree of convective organization and how it changes with warming, does that affect the overall, sensitivity of our climate system, how much it warms in response to an external forcing? The answer is, at least in these simulations, yes, it does. So if we look again across the same ensemble of simulations, here now what's being shown is something known as the climate feedback parameter. Roughly, basically, when it's higher on this axis, it means that that would correspond to a higher climate sensitivity. And we find that it's in fact the temperature dependence of self-aggregation in these simulations that can explain part of the intermodal spread in this climate feedback. So models that become more organized with warming tend to have lower climate sensitivities than models that become less organized with warming, which have higher climate sensitivities, or even, in fact, these ones where this feedback parameter is positive would have unstable climates. This doesn't mean, again, this is just in this idealized set of simulations, but it says that it definitely plays a big role. This is partially due to the effect on the cloud feedbacks I talked about on the other slide, though. If you go back to that, you see that the numbers here kind of range between minus 0.5 and 1.5 or so, whereas the range on this plot is much bigger. So the effect on cloud feedbacks does contribute, but the bigger effect is the fact that when convection is more organized, there's enhanced clear sky outgoing long-wave radiation due to mid-tropospheric drying. And in particular, if we compare the red points here to the blue points, the red points are our global climate models that run on coarser grid spacing and have parameterized convection, versus the cloud resolving models in blue, which are using smaller grid spacing and explicitly representing convection. We see that the GCMs, the red ones, have on average lower climate sensitivity than the CRMs. And this is because, at least again in this ensemble of idealized simulations, the GCMs have more of an increase in organization of warming. Now, from this, we don't know necessarily which one is right. That's sort of an area of active research, though there are some reasons to think that maybe the GCMs are sort of overestimating the degree of organization. So that was a bit, I think, of a whirlwind tour, but about organization of convection and how it affects climate. I think the two biggest takeaway points I want you guys to take away from this talk are, one, that convection is complicated, but understanding it and its organization in particular is really important for climate. And so it's complicated because it's a turbulent motion rather than laminar, which just makes the dynamics more confusing and difficult to express. These small scale motions associated with convection interact with larger scale circulations, and this multi-scale behavior is really difficult to represent in models. Models tend to either do one thing, but not the other. So you can either run a model on a small domain at high resolution to do a good job with those small scale motions, but then you miss the larger scale circulations, or vice versa. Convection organizes across many scales by many different mechanisms. It's strongly influenced by the phase changes of water, and radiation and convection are highly interactive. These have important consequences. So in our climate system, convection dominates the overall heat transport much of the time and sets important sort of baseline properties like our temperature lapse rate. And in particular, the fact that we have a moist adiabatic lapse rate as opposed to a different one has important consequences for climate warming as well, because that's not a constant. It changes with warming and causes the upper troposphere to actually warm more than the lower troposphere, which has other important implications. Moist convection moves water vapor around, affecting the humidity profile, generates clouds. And as I just went over, the fact that it organizes modulates the hydrological cycle, cloudiness, and the energy budget. And so the response, in particular, tropical convective clouds to warming, is something that contributes substantially to uncertainty in our estimates of climate sensitivity. But to end on a more positive note, I think we're at a really exciting place right now in our field, in particular, because of, well, there's been theoretical advances, better observations, but in particular, the advent of global cloud resolving models, which can maybe do better at getting this sort of multi-scale interaction. They present a really rich opportunity for this study of convection climate interactions, especially as it becomes more computationally feasible to run those simulations for longer periods of time. So with that, I'll conclude. Thank you guys so much for attending, and I'd be happy to take questions. Thank you.
Okay, great. Thank you, Allie, for a wonderful talk and a great overview of the richness of the problem. Let's get started with one of the questions that came up in the Q&A. If you want, I can happily read it, or if you want to take a look, Allie, yourself.
Yeah, so
in Q&A.
In dry convection, we can use the Brunt Weissler frequency to check whether a vertical thermal profile is stable or unstable to convection. Do we have a similar stability criterion for moist convection? Yeah, so it's a little bit more complicated in moist convection because you can have things known as conditional stability. So the sort of size of the displacement that you have can affect whether things are stable or unstable. So you could have it be stable to a small displacement, but unstable to a large displacement because of, you know, whether or not you actually get into that regime of having the phase change or not. So it's not quite as simple as just calculating a single parameter like that, but there are sort of versions of sort of stability metrics that have been developed to kind of try to include the effects of moisture. But yeah, the fact that we have that phase change does make the question of stability more complex.
Great. So I'm also happy to open the floor to questions. If you have a question, please raise your hand and I can unmute you and you can then go ahead and ask it yourself.
There's a few more in the Q&A as well.
Oh, really? Okay, great. Yeah, go for it.
Okay, so there's a question about what's my view of the need for resolution in global climate models versus coarser but parameterized models? Should global CRMs mostly inform parameterizations, or should we try to go for higher and higher resolution? This is a great question, and there's a lot of different opinions, I think, in the community regarding the answer to this question. I think, you know, on one hand, from a practical standpoint, it's going to be a long time before we can do like CMIP type simulations that are resolving convection. So we still are going to need parameterizations for a while. And so in that regard, trying to improve them, you know, is a useful endeavor, which can be informed both by, you know, higher resolution simulations as well as observations. I think we, you know, it's not all about modeling. We also need better observations of all of these processes. But I do think that ultimately, you know, we know how to model convection. We can do it if we have high enough resolution. And so in some ways it seems more natural to just get these kind of complex scale interactions, you know, as an intrinsic output of the model rather than trying to parameterize it. So in that regard, you know, going to higher resolution, I think does have its benefit. And, you know, this sort of some of the initial work that has been done using, you know, global cloud resolving model simulations, including, for example, the Diamond project, have shown that you do get really big improvements in many things, such as, you know, the equatorial wave spectrum and tropical cyclones and extreme precip. So there are, you know, a lot of practical benefits to just kind of going for it and resolving convection. But, you know, I think at our current point in time, we probably have to have sort of multiple sort of avenues of investigation. I would say also that I think, you know, we probably never want to completely lose parameterization because, you know, and I think about it when I talk about parameterizations in my convection class that I teach, in some regard, convective parameterizations are an encapsulation of our knowledge of how convection relates to larger scale environments. And so even if they become not necessarily the most efficient or accurate way of representing or simulating convection, they're still useful for kind of connecting to that conceptual and theoretical understanding. And then finally, and just note that, just because we go to, say, kilometer scale resolution and don't need a deep convective parameterization anymore, there's lots of other parameterizations we still will need, potentially still needing shallow convective parameterization. You have to go to higher grid spacing to do a good job at explicitly representing shallow convection because they're tiny air clouds. And it kind of really increases the importance of other parameterizations, for example, microphysics schemes. So, just going to high resolution is not going to solve all of our problems, but it might make them more accurate problems, I guess, maybe in a way. And then there was another question about, given the complexity of convective organization, is there a role for highly simplified models for a better understanding? For example, simplified models of MGO? Yes, definitely. I think so. And that's one of the reasons, that we like to use a hierarchy of models in which you can kind of build from sort of simple theoretical kind of constructs that explain what's happening in sort of reduced complexity models all the way up to the fully comprehensive ones. And you're probably not going to be able to write, a single equation down that explains everything, but maybe it can explain some of the most key elements. And I think being able to do that is a very important part of the understanding piece of the process. And that's in particular why I like doing these sort of idealized simulations where it's like you have the full complexity of all the physics, but the boundary conditions are simplified, because those sort of simulations are a little bit easier to connect to like simple kind of analytic theory than going full bore complex. Okay, and then we have another question. Wondering if there's a connection between the up-ante mechanism and convection self-aggregation RCE invoking the integrated moist static energy framework. What exactly are you referring to regarding the up-ante mechanism in this context? I'm not immediately off the top of my head knowing what the connection is there. The integrated moist static energy framework is a framework I've used to quantify the mechanisms contributing to moist static energy. It sort of takes advantage of the fact that convection is really tightly linked to what moist static energy is doing. But when you column integrate it, we don't have to explicitly consider, convective sources or sinks, because convection is just redistributing moist static energy in the vertical. And so then as convection organizes, as I said, dry regions get drier, moist get moister. That leads to an increase in the variance of column integrated moist static energy. And so we can understand the mechanisms driving that by looking at the budget for that, which includes all of these sort of radiative feedbacks and surface flux feedbacks and advection and things like that I mentioned. And so it's, it's a diagnostic framework. It's not a theory, I guess. But I think it has been useful for quantifying at least the different mechanisms, and it can be applied to different types of simulations and even observations as well. Okay.
All right, that's great, Allison.
Those.
I don't see any open questions and I don't see any hands up, but please raise your hand if there's a final burning question before we close up this first fall seminar of the APS GPC seminar series. Okay, it looks like we've exhausted those questions, so I just want to take an opportunity to thank Allison again for a wonderful talk and remind everyone that this is a monthly series, so please go to the website and sign up for another talk coming up in October. So take a look there. Nice to see you all, and take care and see you.
Thank you for an inspiring talk.
Yeah. Thank you very much. Thanks to everyone for attending and for the great questions. And yeah, thanks again for inviting me.
Okay. Take care. Have a good class.
No, yeah. Yes, I have to run off and teach atmospheric dynamics now. Sometimes.
Right. And this
All
talk
right,
recording
take
will be
care.
online, I think.
Awesome. All right. Bye.
Okay, bye.